So I'd like to talk about snowflakes today and how they grow and why they look like they do. And so there's a lot of reasons to think about this. One is just these things fall out of the sky and they have these kind of amazing shapes. And it's just kind of puzzling why they look like they do. So just out of pure curiosity, we would like to understand where these things come from and how they form and why they appear in the shapes that they do. I first started reading about this subject about 30 years ago, quite a while, and I just found it really fascinating that the physics of this was kind of difficult and not very well understood. And people had not done a lot of really hardcore experiments trying to see what's going on. And so I started thinking about this. And just the more I got into it from the physics of what's happening, it's just more interesting it got. So I've been doing this for quite a long time and making a little headway. Another reason for sort of thinking about this is just that nature always makes things through self-assembly. And so, you know, living things are just masters of self-assembly. All this stuff just appears. And it's safe to say that at least for living things, we don't have really any clue how this works. And so it's very complicated, right? Lots of molecules involved and lots of different processes. Too hard, much too hard. So the question is, can we take a simpler system and understand that? And how simple do we have to go before we can get our head around it and really understand it? And so ice and snowflake formation is just a nice simple example. It's one molecule, mostly just physics and crystal growth. And at least in principle, it doesn't seem that hard that we could kind of fully understand what's going on. Now, to fully understand a condensed matter system it's not something you have to define your terms. And what I want to say is just that we could make a computational model of this. So we would have to have an understanding of all the relevant physical processes, enough so that we could create algorithms and put all this in the computer and then generate numerical snowflakes in such a way that it reproduced reasonably well the known growth behaviors and it would agree with experiments and that kind of thing. So the question is just, can we do that? Can we make something that's very complicated? So we're not going to just write an equation for snowflakes. That's not it. It's 'cause there's a lot of different processes going on. We have to make a lot of approximations. But can we make a model on this? And the short answer is not quite, not yet, but we're getting close. Another aspect of this I kind of like is if you just look at the water phase diagram. If you look at ice growing from water vapor, which is what snowflakes are, then you get to probe this entire line segment here. Okay, and so you can grow crystals as a function of temperature and supersaturation, and those are independent variables. So you're sitting at some point, some temperature here, which is just the equilibrium temperature at that point, and then you go off the line to get a non-zero supersaturation. And so it's a two-dimensional problem. You get two variables you can play with. Now, if you're growing ice from water, in principle, you have another line, and the variables are pressure and supercooling. But this line is very hard to probe. And so we mostly sit near atmospheric pressure, normal pressures, and just look at one variable. It does get interesting when you take the pressure high enough, but it gets expensive. And so this line has not been very well explored experimentally. And of course, if you expand out the phase diagram, there are dozens of these line segments, okay, phase boundaries. And in principle, all of them would be very interesting. And they're all really hard to get to, except this one. This is the easiest one by far. And so, so it's kind of the one you would start with if you wanted to understand phase transition in water. Okay, so I want to start with an experiment just to get our head around the problem a little bit. And this is what I call a snowflake on a stick. And so we're going to start with some environment. We have to recreate this in the lab. So I have a fixed temperature, below zero, of course, and a fixed supersaturation. And we have to create that in the lab. That's the tricky part, but we managed to do it. It's a non-equilibrium condition, of course. So if the supersaturation is 0, then it's stable. So we have to make that greater than 0. And these are done in air at 1 atmosphere. That's convenient. We could do other pressures as well. And so once we make that environment, then ice will grow. And so then we need to add a seed crystal because it's supersaturated. And now normally you think of a seed crystal as being some just little speck of ice, but it's quite convenient to make your needle make your seed crystal to be a long needle of ice. And I'm going to talk later about how we make these because that's kind of fun by itself. But for now, we'll just assume that we've got these, and this one is about 2 millimeters long. And at the tip, it's quite thin, just a few microns in diameter, radius at the tip. And we can make these on demand. And so, so what we do is we have a chamber in the lab, and it's a double chamber situation. There's one diffusion chamber over here and another one over here. And we make the needles in this diffusion chamber, which is optimized for making these needles. And so we get this, something like this. And then we move this thing bodily over into this other diffusion chamber where we have separately controlled conditions. Okay, so in this example over here, we're going to take this needle, move it over into a chamber where the temperature around this point is -15, and the supersaturation is 16%. And then later on, after it grows for a little while, we're going to increase the supersaturation to 64%. So we can just do that. And this is a time-lapse movie. It takes about 20 minutes for this in real life. So here's the low supersaturation, and we get a plate growing on a stick. And then we increase the supersaturation. Whoops, skipped a little in the video. And now we get dendritic branches growing from that. Okay. And we can do this over and over again. This is about 2 millimeters from here to here, roughly. So that sets the scale. They're pretty big. Okay. And okay, so we can do this now by varying both the temperature and the supersaturation at will. Okay, so we can do this lots of different times. And, oh, sorry. Yeah, where'd it go? Boy, there we go. So here's a sort of a two-dimensional grid of these snowflakes on a stick. And so the temperature is down here from -1, -3, all the way to -21. And then supersaturation goes from 8%, 16, 32, 64, 128. The supersaturation is not as easy to measure. The temperature is pretty easy. We just stick a thermistor in. Supersaturation we have to model. And so these are not precise. They're maybe plus or minus 20% on a good day. But nevertheless, it gets the job done. And so what you see is that there's a lot of different structures. Okay, here's your canonical snowflake structure. We can get funny-looking structures over here. Lots of different things going on. And all of these are grown constant conditions. Okay, so we plunk the needle down at some fixed supersaturation and fixed temperature, and the growth times vary. It's shorter up here, longer down here. Typically some minutes to grow these things. Okay, a few minutes up here, maybe 10 or 20 minutes down here. Okay. How reproducible? Okay, so every little nuance of a crystal like that is not going to reproduce, but the overall shapes are very reproducible. Oh, yeah, and it's absolutely, very. Yeah, like for example, this has a lot of little streaks. Those would not reproduce, but the overall these rib-like structures and the plate. Yeah, oh yeah, very clear. It's easy and reproducible. And kind of amazing because, you know, the melting point's way over here. And so we're just changing from minus 11 to minus 13, and it's just a small change in temperature and pretty dramatic change in the morphology. And that's part of what we have to explain is how you can get such dramatic changes in morphology with only small changes in temperature, and that's a big thesis coming up. It's fair. I've done more experiments. We've done every degree, and it's over here half a degree, and it's continuous, but it does have rather abrupt changes, certainly. It disrupts the space-time continuum, and no, we can't make the supersaturation that high at these low temperatures. And in fact, as you go to even higher temperatures, we have problems too, because if you make the supersaturation high, when the temperature is high, then it just melts. Okay, so we have some problems way over here near the melting point in here. But, you know, we do what we can do. So it's just to look at a few examples. Here's one. This is at high supersaturation and minus 5 degrees. And this is these are like 6 dendritic structures. Each one looks something like this. A very complicated looking thing. And the hexagons here are just to give you the axes, okay? And this grows very fast. And it's a dendritic structure, but you're used to seeing dendritic structures with a certain symmetry to them. And this is a different kind of dendritic structure. And again, we have to explain why you get this kind of dendrite over here and this kind of dendrite over here. That's part of the deal. I'm kind of partial to these cup shapes. There's one around minus 7. And this is just a sketch. And what it is a tapered cup. It's very hollow inside and very deep and very thin. The walls here are very thin. It's hard to see from the pictures. You have to roll these around a little bit and look at it from different angles before you can make the sketch. But you know, you look at enough of these things and it starts to make sense. Same with this thing. It's hard to see from one picture. And so this is a cup, hexagonal cup, and then here we have these fins coming down, and they're again very reproducible. We do this all the time. And just a couple of degrees away, you imagine taking this thing and just flattening it out. So now it's more of a shallow dish than a cup. The fins are still here, sort of, but now they got little plates of their own. I call those little I-beam structures because they look like I-beams. And again, very reproducible. We see this stuff all the time. So this is the challenge: is you know, what's going on? There's a lot of a strange behavior. And just what is the underlying physics? These are all growing at constant conditions, so we're not moving things around. But it does give you an indication that it's pretty complicated. I mean, it's not just a simple monotonic thing with temperature. There's a lot of weird stuff going on. So we're going to have some complicated physics to explain it. Say that again. I didn't hear it.
Here now, like there is this cup we've been described, and there's a cube of ice, and that cube is the ice needle that you showed before, or is it part of
this thing? It's not a tube. That's a solid column of ice.
Yeah, but it's the ice needle that you showed before, or is
Yep.
it part of
Yes. Yeah. It's a needle. So yeah, they all start out as needles. Some of them kind of stay needles-like. They don't grow very fast down at the bottom. And then sometimes they sprout these different structures on top. But they all have this needle, and that's just part of the seed crystal. They get fatter with time because they're growing too. Okay. Oh, another.
when you start with the initial ice needle, it's always the same crystal orientation?
Yes, it is. They're all C-axis needles. And there's a trick to that. I'll get to that at the end. We're very proud of that. That's a feature. Affected by No, not so much. Not so much. Yeah, vibration is. You have to really vibrate. Now, airflow will affect it. Chemical impurities will affect the growth. Lots of things, but. All right, so again, we're trying to the goal is to understand this well enough that we could make a comprehensive numerical model where you would just give me a temperature and a supersaturation, and I would plug that in, and lo and behold, this would grow out, and all of these things. And so we have to have enough complexity, and we have to understand the underlying physics enough that we can make that happen, okay? And that's a bit of a challenge, turns out. I also want to point out that these things are not just laboratory curiosities. You can go outside and see these things if it's snowing. If you ever go skiing, this is a good thing you can do on the chairlift. You bring a little magnifier, and you can really nerd out. You're just sitting there like this. And so columns like this, these are hollow columns, and there's the little sketch. They grow around -5, and you can see that in the other pictures. I took these pictures. I spent a lot of time doing snowflake photography over the years as part of my slightly unhealthy obsession with this subject. I built a microscope, and I live in Los Angeles, so there's like 0 snow. So I have to go, but that's okay because the best crystals grow where it's pretty cold anyway, where no one wants to live. So I built this thing. It's kind of funny because normal microscopes have they're a little too high resolution, and macro photography is just a little too low resolution. So you can build something that just hits that sweet spot, and I sort of lived through a transition where it went from easy to really hard to get this through airport security. So here's, again, at -5. This is just higher supersaturation. You get needles and needle clusters. So this one was a hollow column. You can see the little hollows in there. And then it branched, and you get these needles. This was just the windshield of my car one morning. Sometimes you get nothing but needles. These are fairly small, a couple of millimeters in length. So you don't see them if you're not looking for them. If you're skiing, you see what they look like is little tiny white hair, little snippets of hair on your sleeve, and you have to look at them pretty carefully to see the structure. You can definitely make some of it out with a little magnifier, a hand magnifier, but really want to get into the details, you need a microscope. Okay. These are also kind of strange looking. These are called capped columns, and it's a column, and then later on it turned into a plate. And these did not grow at constant conditions. The column grows around -6, and then the plate's around roughly -13, give or take. And these are quite easy to find if you go looking for them. When I first started reading about this subject, I grew up in North Dakota where it snows all the time. And so I witnessed tons of snow and never saw anything like this because I never looked. And, you just don't look sometimes. And I read about this, and I was visiting North Dakota, and I went outside, and I found these after an hour of looking because they're there. They're pretty common, easy to find if you go looking for them. Here's some really bizarre things. Wait a minute. Yeah, okay. So these are, it gets weirder. These grew at very strange conditions. I got these in Fairbanks one time. It wasn't very cold, but the growth went from a column to a plate to more columns. And these fell pretty consistently for about 15 minutes. Not all looking like that. Most of them look like little globs of stuff. But these were mixed in. And so that, like 15 minutes, you could see these, and then they were gone. And I only saw those once ever. So, oh, yeah, absolutely. Yep. Yeah, yeah, well, these, they fall out of the sky. You don't know where they've been. And there's lots of inversion layers in Fairbanks. And of course, your standard holiday snowflakes are out there. If you want to see these, they only form in a narrow temperature range around -15. And that's the temperature up in the clouds. So it might be -13 or so at the ground. A little warmer usually at the ground. And these are not so easy to find because they just don't happen that often. You need, well, also, -15 is cold. You're not going to go skiing when it's -15. That's about the edge of civilization. When you when you go to -15, you find that people who live there wish they weren't there in January. So some of these I got in northern Sweden, up at Kiruna, which is above the Arctic Circle, and that's really how far north you have to go in Europe to get really nice looking crystals like this. Okay, so this is nothing new. People have been looking at these for as long as they've been looking. I mean, for centuries. And so people see all kinds of funny things, and they've given them names. First thing you do when you see some phenomena you like, you start to name them, because at least when you name them, then you can talk about them. But there are, and so sometimes people ask me, how many different kinds of snowflakes are there? And that's like asking how many different kinds of bread are there. I mean, there's an infinite number depending on how you define bread, or named colors. How many colors can you name? You can name as many colors as you want. But there's a few standards. There's red and blue and orange, and same thing here. There's a few standard shapes. Now, if you're interested in meteorology, this is what most of the snow looks like. So, if you think these shapes matter very much, not so much. This is what most snow looks like. With one exception, I've talked to people who do a lot of powder skiing, and these fern-like stellar dendrites are a favorite. They pack very, very loosely. And so the powder skiers, the real dedicated powder skiers, they know to look for these. And when they see them, they got to get their skis and go climb up and ski on it, because in a day or two it all packs down and then it's no fun anymore. So that's like the only time it really matters. -15, so cold. You gotta be dedicated if you're a powder skier. Plus you gotta go way up high where nobody's gone before. So when you pack the snow at a ski resort for downhill skiing, it all looks like this. So no powder skiing at ski resorts unless you go away from the ski resort. So where do you start? What do you do with all this? After you've named some of these things, you start to study them. And the person who really started doing this the first time, a scientist who really looked at the snowflakes as a science project, was A.Huerre Nakaya in the 1930s. And it's a wonderful story if you're a young person looking for a job, because Nakaya could not find a job to save his life. He's a nuclear physicist, and he could not get a job in Tokyo where he really wanted it. And he got a job in Hokkaido University, which was just like the Arctic Circle back in the 30s. He's far, far away. And so he couldn't couldn't collaborate anymore with people that early, no Zoom meetings. And so he started studying snow, which you get a lot of in Hokkaido. And he became very famous for this. He did a lot of observations of natural snow. And then he got a walk-in freezer, which was very new at the time. And he started growing these things in the lab. And he grew them on these little rabbit hair and wrote a book about this. And he described the morphology as a function of these two variables, temperature and supersaturation, because he could recreate that in the lab. And so this is now called the Nakaya diagram, okay? And it's kind of an empirical thing, and it's qualitative. It just gives morphologies. But it's become kind of a Rosetta Stone. I call it the Rosetta Stone for snow crystals, because when you have this diagram, now you can understand kind of what's going on when you look at crystals falling from the sky. So you see these trends. I mean, at very high temperatures, and we saw this in that plot I showed you before, the matrix I showed before. You get plate-like crystals when the temperature is just below freezing, and then columnar crystals around -5, -6, and more plates, very thin plates around -15. And if you really go lower in temperature, down here around -50, -60, you get columns again. So there's these transitions from plates to columns, which is pretty weird. And on top of that, on the other axis, you've got very simple morphologies here, just faceted prisms mostly, when the growth is very slow. And as you increase the growth velocity, the supersaturation, you get more and more complexity. And that we can understand from diffusion limited growth, and we'll get to that in a minute. So when you're looking at something like this needle cluster, you can immediately see, its history to some degree. It started out as a needle cluster, that's right here. And then it grew these plates, and they're seen edge on here. So these are thin plates, so that's maybe around here. So it started here, and it moved here. Okay, that's what happened. Why did that happen? We don't know. But I mentioned before that cap columns are easy to see, and that's because this kind of transition happens all the time in cold fronts. So you got a front of some kind, and the characteristic of a front is you have some warm, moist air, and it gets pushed upward by, in this case, a mass of cold air. And so when it gets pushed upward, these clouds start to get colder. And so they have liquid water in them. These are liquid water droplet clouds. And as they move up, they get colder, and they come up down here, and they don't freeze right away, but they will start freezing around -5, -6, and that will produce the columns. And then as they keep rising, it'll transition over the plates. And so you see these kinds of things a lot because this transition, this flow of air happens a lot during storms. Okay, I want to spend a lot of time on these temperature transitions, and this is what I call a very robust result. You can do this experiment, lots of different experiments, and see this very easily. Here's one we did in the lab. It's a very low budget experiment. We have a tank. It's maybe a meter high, and it's got it's just a tank with empty, got air in it. And we get the whole tank cold. We got a chiller that heats the outside. So the whole tank is whatever temperature we want to make it. And then we put a little bucket of water in there and heat the water. And that causes the water vapor to evaporate. And convection mixes this because it's warm here and cold everywhere else. And so the air is mixing a lot. And that creates a fairly uniform supersaturation inside this tank. Not super uniform, but uniform enough. And then we have a nucleator on top. That's just a little thing of, got a little compressed gas in it, a constriction and a valve. And so you get a little pocket of compressed air. And then you open that valve and it expands very rapidly and gets very cold locally and just erratically and just very non-linearly. It gets very cold when you open that valve. And that makes the supersaturation go up very, very high, somewhere around here. And that will cause crystals to nucleate, okay? And when they nucleate, they start to grow, and they'll just fall and grow. And some of them will fall on the substrate, and we can have a window and put a microscope underneath. And so here's the result. If we have this tank at -2 plates, and again, here the supersaturation is not very uniform. And so we get a lot of different structures, a few columns, mostly plates, mostly thin plates. If we go to -5, we get columns, lots of columns, some weird stuff. It's not very clean in there either. This is a low budget experiment. At a -15, clearly nice thin plates. Here's an edge-on view, very thin and flat. Okay, so again, we see these transitions from plates to columns to plates, very reproducible. After Nakaya did this, and published his results, people done it numerous times, many different ways. You always see the same stuff. It's very reproducible. So there's just no question that this is right at some level. Okay, and that's important to say in this business because all the experiments are kind of hard, and you have to look for what I think of as robust results that you really trust. And the Nakaya diagram is absolutely trustworthy at some level where, it's a little bit qualitative what's going on. Okay, so let's talk about just the basic model of how snowflakes grow. This is pretty simple stuff for this crowd, but, it pays to start at the beginning. So you start with clouds, which have liquid water droplets in them. And now the cloud is getting cold, and the droplets will start to freeze at some temperature, around -5, 6, something like that. And the droplets don't all freeze at the same time. Each droplet has a piece of dust inside because the droplets nucleate on a piece of dust in the atmosphere. So some dust in every droplet, and that dust does a dual duty. It also nucleates the freezing of ice. And so each droplet has a different piece of dust, and so they will freeze at different times. So one of them will freeze at some point, and when it freezes, it starts to grow by absorbing water vapor around it, and that depletes the air from water vapor, and that causes the other droplets to evaporate. And then as it grows, more droplets evaporate, and the crystal grows until it's big enough that it falls. It takes about 100,000 droplets evaporating to make one snow crystal. And this is kind of the roundabout way where you take liquid water in a cloud and turn it into solid water on the ground. It first goes through the vapor phase. So the liquid evaporates into the vapor phase, and then the vapor goes into the ice crystal. So, I mean, sometimes the droplets can freeze and produce cirrus clouds, okay, ice clouds, but this is the way it happens in a normal snowstorm. Okay, so if you want to look at the physics, there's two main pieces of physics that are really important. One is the attachment kinetics, which is just how the water molecules stick to the surface. Okay, so we know what the ice crystal looks like. There's the water molecules, and the structure of that's been known for 100 years. There are two principal facets, a basal facet and two basal facets and six prism facets. And so this little hexagonal prism is kind of the hydrogen atom of snowflakes. It's the simplest thing you can make. We see these falling. They usually have some structure. We can make them in the lab very easily. And so the way the faceting happens is you start with just any shape you want. And if you look at the structure, there's these the flat surfaces. The faceted surfaces are very flat, and so there's not much to hang on to. And so a molecule will bounce off that surface because there's just not a lot of dangling bonds. And in the rough regions, there's more bonds available. And so these little nooks and crannies are where the molecules preferentially stick. And so you fill in those rough areas, and you end up, no matter how you started, you end up with a faceted crystal. Okay, and so it's just that it's nothing to do with the surface energy. It's really, except indirectly, it's mostly just this attachment kinetics, which is the rate at which these molecules will stick to the surface, and the rate is just much higher in these rough regions and much slower on the surface, and that can be 100 to 1, 1,000 to 1, depending on conditions. Okay. And it's all just a non-equilibrium process. Surface energy, it's actually pretty isotropic, and we don't have to worry about that. But the attachment kinetics is highly anisotropic, and that's what makes facets. And so, that's why there's no funny-looking snowflakes. And the faceting is how the geometry of the water molecule is transferred to the geometry of a snow crystal, because the molecular physics is all very local, but it produces on very large scales this a faceted crystal where one corner is the same as the other, just because they're all operating on the same rules. Okay. So the second thing that's important is diffusion limited growth, and so we have particle diffusion. Okay, so the water vapor has to diffuse through the air. When the crystal's growing, it sucks the water vapor out of the air, depletes the air around it, and so there's just not much water nearby. So the water has to diffuse down from far away to get to the crystal, and it will do that because there's sort of a hole and in the water vapor. And these corners stick out farther, okay, and so they will preferentially attract water molecules. And so if you turn up the supersaturation or make the crystal big enough, these corners will sprout and form branches. The Mullen-Sakarica instability, which we've heard about already yesterday, and that's a positive feedback. Once the molecules start to stick to the tip here, then the tip will stick out farther, and then it gathers even more and sticks out further, and so you see a faceted crystal will develop these branches, and the branches will develop quickly and produce a growth instability. Okay, and then once you've got these main branches, then you can get additional instabilities on the sides, so you can get branching and side branching. And there's just a huge amount of literature in the scientific literature on diffusion and limited growth, and I'm not going to talk too much about it, but it's definitely a big part of the process. And here's two examples again. Here's a plate-like dendrite. This is thin. Now remember, this is a thin, flat crystal. We call it a snowflake for a reason. It's thin and flat. So the basal surfaces are not growing very fast, and that's the attachment kinetics. But the prism surfaces are growing very rapidly, and so they will start to form dendritic structures. And at -5, it's a little more complicated. You've got a weird combination of kinetics and diffusion limited growth to produce a funny-looking three-dimensional dendrite. And so it's this combination that's making all the structure. So here's your sort of canonical model of how you get a complex but symmetrical snowflake, 'cause, right, they're always kind of symmetrical, often kind of symmetrical. They can be symmetrical. So you start with the nucleation of a particle, and it grows into a prism at first because the attachment kinetics are important, most important when the crystal is small or the growth is slow. And so for a small crystal, you tend to get a faceted prism. And then as the crystal gets bigger, or if it moves into a region of high supersaturation, you will sprout branches. And those branches will start to grow out. And then now it's moving to lots of different conditions. It's just blowing around in the cloud. And sometimes you get, in this example, plates growing on the ends of the branches because the supersaturation fell down a little bit, or the temperature changed. And so each time it's moving around, something different happens. The growth is mostly at the tips, at the outer regions. And so each time the crystal moves, something happens. And so you get if you have a crystal with a complex history, because it's just blowing around in the clouds, then you get a complex shape. And because you have both kinetics and diffusion, you can get faceted and branched structures. This is sort of a combination of both. But each arm has the same history. So this arm grows more or less the same as this arm, only because they saw the same things at the same time. They don't talk to one another. They just see the same things. And no two paths through the clouds are exactly the same, so no two snowflakes are alike. And so you can kind of understand why you get such a complex diversity of morphologies, at least for these kinds of crystals. But of course, what I described is really this little piece here. You can get faceted and then branched, and you can go back and forth a little bit. But that's only a very rough model that doesn't include any of this temperature stuff. So obviously you need a lot more to this problem. And so we have to really look at both the kinetics and diffusion and understand them both pretty well to really be able to make some progress here. So now let me talk about diffusion and diffusion limited growth, because that's a big player. Okay, and that's mostly responsible for the structure, the complex structures, especially branching dendritic structures. And we're all familiar with diffusion outward. This is diffusion inward. Okay, so you've got a supersaturated medium, the air, with water vapor, supersaturated water vapor. And then the ice crystal, once it forms, once it nucleates, will just remove water vapor from the air around it and create kind of a hole, which is the origin of the diffusion limited growth, right? The diffusion is of the water vapor to the crystals what limits the growth. And you can see this directly. Here's a simulation, a computer simulation of a growing crystal. It's a two-dimensional crystal, and the physics isn't exactly right, but it does make, say, branched and faceted structure. Turns out it's a lot easier to make some kind of branched faceted structure than to actually make all of the branched faceted structures. So progress, one crystal at a time. But the outer part here, the darkness of this region is proportional to the supersaturation. So the supersaturation is kind of high out here and then very low near the crystal. Real crystals have they're not quite so tight in because of the three-dimensional tends to be more of a spherical shell of low supersaturation. Okay. Let's see. So anyway, you can sort of picture what's going on. Here's another example from my lab. And so here what we have is a substrate, piece of glass, sapphire actually, and you drop a crystal, a little seed crystal on the sapphire and now blow some moist air down onto the substrate. And what happens, far away from the crystal, the supersaturation is high enough that you nucleate water droplets. So this fog, that's all water droplets. But here, the crystal is sucking the water vapor out of the air. And so in this region here, there's no condensation of water droplets. It's not high enough. Supersaturation is not high enough here. And so you see this edge. And that edge delineates where the supersaturation is equal to the water supersaturation, where you'll start to condense water droplets. And so again, it gives you kind of a visualization, high supersaturation and low supersaturation. Okay. Yeah. It does, and it causes this crystal to grow. And there is water, the vapor pressure here is above the, it is supersaturated right here, and so the crystal will grow, but it's not high enough to nucleate droplets. So it's a complicated three-dimensional problem. I wouldn't want to try to analyze it. But yes, you're certainly blowing air down, and there is supersaturation everywhere. It's just that here it's high enough to make droplets, and here it's only high enough to grow the crystal. So. So, of course, you have to really get serious. You got to solve some equations. We know how to do this. Diffusion equation is pretty straightforward. We know that one, and we get to use the Laplace approximation, which is just del squared sigma is 0, where that's the supersaturation field around the crystal. And the reason we get to do that is that the time scale for the relaxation of the supersaturation field is much shorter than the growth of the time of the crystal. So it's called the Peckley number, that ratio, and the Peckley number is very low, 10 to the minus 2, 10 to the minus 3. So we can really ignore the crystal moving and just have the del squared equals 0 around the crystal. So that's just a Laplace approximation of the normal diffusion equation. And so it does make it a lot easier to solve. Everybody knows how to solve this. It's very easy to write this into a computer program. So that's great. So we have no problem solving the diffusion equation around the crystal. The trick is the boundary conditions, which do change slowly. But mostly they're just complicated boundary conditions because it depends on the shape of the crystal. And for that we need the attachment kinetics. And so we write it using what's called the Hertz-Knudsen relation, which is just a variable change of sorts. The velocity depends on the supersaturation at the surface. Okay, and you scale it with this kinetic velocity, which is just a scaling factor that depends on all of the statistical mechanics and the ideal gas laws that govern this. So alpha is just a dimensionless number that can go from 0 to 1. It's called the attachment coefficient. You can think of it as a sticking fraction. If a molecule hits a surface and it sticks, then alpha is 1. If it hits the surface and bounces off, then alpha is 0. And so we put a lot of physics in that alpha term, because alpha can also does depend very strongly on sigma. So really we've just changed variables. We've taken velocity as a function of sigma surf and just written it this way, separating out one term of sigma surf, just a well understood number, and then put all the physics in alpha of sigma and T. Okay. It's just a constant. Alpha contains all the real physics, and V kinetic just contains the mass of the water molecule and KT and stuff like that. Okay, easy to derive, but not very interesting. Okay, now I like to do the spherical solution. That's really easy to solve, and no, sigma surface is not zero at the surface, because when there's a facet, for example, it grows very slowly. And so if you have a really slow growing facet, that's just like a piece of glass, and the sigma surface is the same as sigma infinity. The boundary conditions are mixed. You've got the, this gives you alpha times sigma, gives you the velocity, but the velocity is also given by the gradient of sigma. And which is? There is a gradient. There is a gradient in sigma, but we don't know what it is. So the boundary condition is that this velocity is equal to the diffusion, the velocity you get from the gradient of the supersaturation. So that's called mixed boundary conditions, right? You don't fix. Yep. Yeah, it's an interesting problem, you know, but you can't. It's not going to strive every detail, okay? That distracts from the story. So you can also add lots of other things to this, because the sphere is easy to solve. We can add latent heating and heat diffusion, because when you are growing this crystal, you're dissipating heat, and that heat has to go somewhere, and it diffuses outward. And so now you have particles diffusing in and heat diffusing out. It's a double diffusion problem. But for a one-dimensional sphere, piece of cake. I can solve it. We have surface energy from the Gibbs-Thompson effect, which is just that the vapor pressure is dependent on the radius. And we can put that in as well. And we can solve all this. It's very easy analytically. And if you want, I mean, a lot of times we grow crystals on a substrate, and you can take the same solution and use it as a hemisphere. And that is useful for understanding growth of crystals on a substrate. Kind of the same math, basically. So you do all this. You just put all this together and see what's going on. And you can easily reach the following conclusions: that if you're growing crystals in air, the main thing you have to worry about is the attachment kinetics in this alpha and particle diffusion. Okay, thermal effects from heating are minor. They're not zero, but they're not very big. Surface energy effects are also minor and not zero, but mostly you could ignore the surface energy if the radius of anything is greater than a micron. So the surface energy comes into play at, say, the edge of a very sharp, a very thin disk. But for a large crystal, it's just irrelevant, so we can ignore that. But again, you know, these effects are there, and but these are the big players. Okay. Now, if you grow in vacuum, I like to grow a lot of crystals in vacuum. Then the reason for doing that is the diffusion is quite fast. So particle diffusion is not so much of a problem anymore. Then you have the attachment kinetics, which has not changed, plus heat diffusion, because you got to get the heat out. And if you don't have any air, you got to get it out somewhere. It usually goes to the substrate, but heat diffusion becomes important if you're growing especially large crystals, millimeter scale crystals on a substrate. We tend to grow tens of micron scale crystals, and a lot of these problems are much reduced. But the spherical solution is like super useful for understanding the basic physics. For example, that thermal effects, you can mostly ignore thermal effects. Now here's what I mean by mostly ignore. There's another solution. Of course, we can write down a cylindrical solution. You all remember cylindrical solutions in E&M. Same thing, just some logs thrown in. And we can again solve the double diffusion problem analytically for heat and particle diffusion. And here's an experiment. This is a needle, and the needle is growing, and it starts to develop some stuff on the top. But we're going to take this line here and measure the radius of the needle here. And that mostly gets rid of this stuff. Although when you get to the end of it, it starts to deviate. But if you look at the radius as a function of time, it has some nice, smooth, fairly well understood line, which is just the power law you get. For a sphere, it'd be root time. It's similar for a cylinder. And so we draw a line through that and just fit a line through that. And then we can say, well, what is the velocity when the radius is 5 microns, just by looking at it here. So that gives us now a fixed radius. And then we can do this as a function of temperature and supersaturation. And so we can look at the velocity of growth as a function at its fixed radius, and it's as a function of supersaturation. And we can put in a parameterization of that, and we end up with just a single parameter that describes all this growth, which is some coefficient of the fit. Okay, and so what we end up with is we do so we're going to fit this parameter, which is just like this, very simple curve. And if we have both particle and heat diffusion, we get this line, which is analytically derived. And if we throw away heat diffusion and just have particle diffusion, which we can do in theory, then we get this line. So when you add heat diffusion, the growth is slower because the heat's the crystal, and you've got to get rid of that heat. Out here around -15, it's pretty small. It gets bigger as you get close to the melting point. And so this is a non-trivial effect, but believe it or not, a factor of 2 in this game is the least of your problems. So out here, we can pretty much scale it away just by changing the supersaturation. You can model it, it's not so bad. On a substrate, it's much better because with the substrate, we suck all the heat into the substrate, and so now the heat diffusion is kind of irrelevant. Okay, but nevertheless, this is an example how you can use the analytic solutions, and you can compare with experiments, and you get the answer you think you should get. And if you don't, then something's really wrong, because this is just plain diffusion, heat particle diffusion. If you can't do this right, then something is very much amiss, because we understand this, and it works. Mollin-Szekerke instability, we know all about that in this meeting, but I got a slide for it anyway. And so you know the drill. You start out with a 1D solution of the diffusion equation, and you get the crystal growing upward at some constant velocity, but it's unstable. You can put a bump in, and that'll grow faster. And and what's kind of fun about this is, I mean, as an undergraduate, we solve a lot of diffusion equations, and we're always kind of like, once you got the solution to the equation, you're done. But what they don't tell you is that just because you have a solution does not mean it's a stable solution. And when you go into the crystal growth game, you soon find out that very little is stable. So flat growth is unstable, the spherical growth is unstable, everything is unstable. Okay, so you do not get these simple solutions for very long. They will become unstable and produce very complicated solutions. And that's just something you have to deal with. And that's why, if you really want to make progress, you have to, in comparing with experiments, you kind of have to make these computer models to get a handle on this, because you can't just write down analytic solutions anymore. There's another solution to the diffusion equation, a little less known, the Avantsov solution from 1947, and that is similar to the spherical solution, except it's in parabolic coordinates. You remember parabolic coordinates. That's the coordinates you learned about and quickly forgot because you just never wanted to use them again. But in this case, it's a really important solution. And what it looks like is you have a paraboloid of revolution, so in 3 dimensions, and this tip, and you solve the diffusion equation for this thing, and it's a perfectly legitimate solution. just like the sphere, cylinder, it's just different. And what you get is the tip has a constant velocity, and the tip velocity is proportional to 1 over the radius of the tip, and the tip radius is constant in time. Okay, both of these are constant in time. Okay, now this solution, perfectly fine solution to the diffusion equation, known for a long time, is also unstable to the Mollins-Szekeres instability. And so if you grow these things, you get what are called free dendrites. And free just means unconstrained, right? You've got this thing growing into a medium. You can grow ice into liquid water. You can grow ice into air as like this. Lots of things. And if you look at the whole thing, you've got side branching and it's a mess. But if you really focus on the tip, it actually looks kind of like a paraboloid of revolution. Sort of parabolic, it's pretty small. And if you just focus on the tip, then you can use this. And you just ignore the side branching because you can sort of say, well, that's a little like the whole thing as a paraboloid. And it's okay. It's an approximation, but it's not too bad. And this led to, now people started doing this in the 80s with liquid solutions. And this just blew up in the 80s. It was really fun to read the literature because people started doing these really nice experiments and you could not explain what was going on for the longest time. And some really smart people had to think about this hard and came up with what's called solvability theory. And I'll show you what that kind of does, because it's an interesting part of the story. So you start by growing, in this case, these are dendrites growing solidification of a liquid, succinonitrile, just some nice, convenient experimental material, nice, convenient temperature. And you grow free dendrites and you focus on the tip, and you find, lo and behold, you have a fixed paraboloid growing in a moving frame, and everything's just hunky-dory. But if you grow them slowly, you get a low velocity and a large tip radius. And if you grow them at high supercooling, you get a high tip velocity and a small tip radius. And what puzzled people right away was that this event-soft solution says that the tip velocity is proportional to 1 over r, and that's true in all of these. If you take r v tip, you get a constant. But it's a family of solutions. The diffusion equation does not tell you what r or v tip will be. It's just that it has to be one of this family. And it is. These are all in that family. And so the question at that time was just, well, what selects the experimental solution? This is called the selection problem. And again, this went on for years. Not too many years, 5 years, but it was hard. I mean, you read the literature and people were really struggling with this. And the diffusion equation was not enough to solve this, okay? The diffusion equation alone just gave you a family of solutions. And so you had to have some new physics to select the right solution, the experimental solution. And the way you can, well, what turns out to be, there's 2 possibilities. It can either be the attachment kinetics or the surface energy. And so if you take a spherical system and you calculate the velocity as a function of various parameters, okay, you get the velocity is some constant, and there's a supersaturation in there, divided by the radius. That's a normal spherical solution. V goes like 1 over r. But you're doing now we're going to do a Taylor expansion as a function, and Taylor expand on alpha and d. This gives Thomson length. Okay, so we've got, if alpha is high and d is 0, no surface tension, then you just get the normal solution. But both these effects will reduce the velocity, okay? Because if alpha gets small, then this term gets big, and it starts to, this goes to 0, or gets smaller. And similarly, if d is, well, this also gets smaller as r gets smaller, okay? So you get a 1 over r, and these are 1 over r squared terms, and they will tend to restrict the growth, okay? And now, you know, one thing you think is that you would just like get the maximum growth. If r is small, if r is large, then the growth velocity is slow because of this r. But as r gets much higher, then these terms will kill the growth, and there's some maximum growth velocity as a function of r. And you might think that's it, but that's not it. It's not the maximum. Much more complicated than that. I was down in San Diego one time, and I was talking to one of the originators of solvability theory from the 80s. And I asked him, it's like, well, you know, I want to make a slide. How do I describe this? And he just looks at me and grins, and he goes, oh, you're an experimentalist. You don't understand. The theorists won this one. There is no easy answer. And, you know, you basically took this stuff, and you packed it all in your suitcase, and you wandered out into the complex plane for about 40 pages of weird-looking integrals, which I never understood. And the answer pops out. And these guys all agreed on the answer, so who am I to say it was not right? So off we go. And what you find from the solvability theory, which when people figured it out, they were all happy. So I don't really understand it, but I'm willing to quote it. So if surface energy is the dominant term, this guy, then you get the tip velocity goes like the supersaturation squared, and R goes like 1 over sigma. And in this case, it'd be for supercooling, and that's supposed for liquids. This holds for liquids mostly. Okay, so all the metallurgy stuff and the succinonitrile, this is what you get, something like that, roughly. Here's a picture of ice. This is grown in a pond. This sits on the surface of the pond, and you get dendritic growth, and you can look at the tip. And sure enough, you get something like this in ice. This is a mixed system because the basal facet grows very slowly, but nevertheless, this is a pretty robust theory. And so even if you make a lot of weird changes to it, you get similar answers. However, if the tip growth is limited by attachment kinetics, if this is the dominant term, we can ignore that guy, then the tip velocity goes like not the second power, but the first power, and R is constant. And that tends to hold for vapor growth, mostly. And that's for anything growing from vapor. So if you're growing from liquid, you tend to get this solution. If you're growing from vapor, you tend to get this solution. There are caveats and exceptions, I'm sure, but that's kind of the way it is. And so we can look at ice. We can grow these dendrites. We can grow minus 15-degree dendrites. These are fishbone dendrites. You always get the same answer. And here is the growth, the supersaturation, and growth velocity is a function of supersaturation, and it's linear. And so this fits. And if you look at the tip radius is always constant. It's around a micron. Okay, can't quite measure it, but it's always around a micron. It looks like it anyway. And so this is the right answer for ice crystal growth. And it can confuse you if you're looking in the literature, because 99% of the literature deals with growth from liquids. Just like at this conference, we are growing crystals from liquids. Ice from liquid is the normal thing, but growing ice from vapor gives a different answer. You don't see much of this in the literature. Once people figured this out, they stopped. Didn't worry too much about this problem. Another thing that came out of this whole effort of solvability theory is that the anisotropy was critical. If you do not have any anisotropy in the crystal, then the solutions are unstable to what's called tip splitting. So if you add some anisotropy, either in the attachment kinetics or in the surface energy, then you can get, and for six-fold symmetry in this case, you get these tips which grow, and you get the Ivantsov solution. But if you take that anisotropy away and go to zero anisotropy, now you get a seaweed structure, or a tumbleweed structure. And that seems to be a universal truth in this theory. And it turns out the radius of that tip, therefore, it depends on the anisotropy, which is very hard to know for any real crystal. So at that point, it became so hard that you couldn't compare with experiments very easily anymore because you didn't know the parameter to put in. And so people kind of lost interest in the problem. So nevertheless, we have these solutions, these conclusions from this theory. Fascinating theory. People worked hard on it. One is that these stable parabolic tips require some anisotropy, crystal anisotropy usually. And so most experiments with real crystals, they have some anisotropy and they produce nice dendrites. you definitely see this if you start growing a crystal on the computer and you take away all the anisotropy, then you don't get a nice parabolic solution anymore. And the surface energy usually dominates from the melt, and attachment kinetic usually dominates in growth from vapor. And if you really want to understand any of this, you got to go to 3D simulations, because it's just really hard to model this using analytics. And also if you see facets, that usually means you've got anisotropic attachment kinetics. And we see this a little in ice. This is a fern-like dendrite growing at extremely high supersaturation, as high as we can make it. And the tips, early on when the supersaturation was very high, they split. So we do see tip splitting on occasion, as theory predicts. So alpha is very, very near 1 when you get to these super high supersaturations. All right, so let's look a little at some examples just of diffusion limited growth. We have fern-like stellar dendrites. Again, we saw these very thin and flat if you look at them from the edge. Rapid growth, the faster the growth, the more erratic the side branching. We always think of snow crystals as being symmetrical. These are not symmetrical. The branches, side branches are very erratic. Okay, so just highly unstable growth. But diffusion limited growth does not explain the flatness. Okay, you cannot make a plate with diffusion limited growth. If you try to make, if you have isotropic attachment kinetics, you always get a round structure, a seaweed structure, a tumbleweed structure. The only way to get a flat structure or a needle structure is to have anisotropic attachment kinetics. So that's just a rule. And here's a really big snow crystal. That is the world's largest documented snow crystal. 10 millimeters from tip to tip. Lots of branching. 10 millimeters from tip to tip. It's a big one. Northern Canada. Found that one in northern Canada. Got to be very calm. Another thing is you just get what I call the competing forces of order and chaos, good and evil. The large-scale morphology is just dominated by the attachment kinetics. Plates, columns, that's all attachment kinetics. And slow growth, you get faceting. The complexity, it comes from branching, and the diffusion limited growth, that's chaos. And the faster the growth, the more chaotic. And so large scale anisotropic kinetic energy and kinetics is very important. Surface energy is not so important. And when those two forces are kind of equal, you get a combination of branching and faceting, and that's what really gives you these really gorgeous structures. And this usually involves changes in the temperature. This one can grow conditions. This can grow at constant conditions. This usually requires changing conditions to sort of flip between the two. Hollow columns, easy to explain. We start out with a column, and the prism facets remain faceted because of attachment kinetics. The basal surfaces have a high alpha, and so they're susceptible to the Mullen-Sakaric instability, and so the edges grow faster, and you get a columnar, hollow columnar crystal like that. So, and here you have a hollow column, which the hexagonal tips broke up into dendrites in separate pieces. So all of that you can explain pretty well. Yeah, you can predict the angle of the cone if you know enough about the attachment kinetics. Yeah. Oh yeah. Yeah. We don't really know how to do that yet, but you can. I mean, if you knew all that and put it in the code, it would work, guaranteed. Bubbles, you sometimes see bubbles. And what's kind of funny is, so here you have a hollow column and then it closed up. And so it's like, well, was it are the edges unstable or not? I mean, they were unstable for a while and then they closed up. And the reason is you just turn the growth down. And when you turn it down, the exterior parts continue to grow very slowly because there's a nucleation barrier. But the interior has no nucleation barrier because there are always these internal kink spots. And so near the edge, it can grow in. So you can get bubbles in columns. And that happens in plates too. You can get hollow plates, and the hollows can fill in and make bubbles. Here's a great example taken by Don Komrechka, a very somewhat internet famous snowflake photographer, using a shutter that produces, and these are interference fringes. So these are sort of micron thick plate-like bubbles in the ice. Kind of cool. And they come in various thicknesses, and he sees a lot of that. If you shine a flash on it, you get double reflections and interference fringes. Here's another weird one. These ridge-like structures, you see them all the time in snow crystals, natural snow crystals. We see them in the lab as well. And they're a little puzzling until you start to sort of figure out what's going on. Here's one we made in the lab. It's called a plate on pedestal snow crystal. We've got a little pedestal down here, and a plate grows out from that. The top surface is quite flat. The bottom surface is convex. And these ridges form on the convex surfaces. So if you flip this over and look down on that convex surface, these you can think of as the molecular steps, because there are steps here. And these are also unstable to the Mullen-Sakerka instability. And so the tip here sees a higher supersaturation. So the step grows out a little faster. And you get this confluence of all these little tips in the one molecule high steps, and that produces a ridge like this. And these will grow out stably if you just grow it for a long time. So you can explain all that. It's, you got to model it to really get it right, and we don't quite know how to do that. We've seen a little of that. Okay, so one last thing I'll try to go fast, a little too fast. So how you make electric needles is kind of fun. We started with this supersaturation in the chamber, and you put a wire in. This is the wire. And the wire just gets covered with frost because crystals grow supersaturated. Then we put 2,000 volts on the wire, and these needles just come shooting out. And they're growing at 10 microns per second, sometimes 100 microns per second. The tip radius you can calculate is like 100 nanometers. That's the smallest. So they're really quite phenomenal. We can, with a little coaxing, we can get C-axis needles. And then we just remove the high voltage, move it to a second chamber, and then we get normal growth on the needle. Okay, and these were first discovered in 1963, and then we kind of figured out some of the theory behind this, because solvability theory didn't exist in 1963, but it did when we started doing this. So we applied it, and we figured out how to make C-axis needles as well. So the theory is kind of fun and not obvious. So the obvious but wrong way is you have an electrically enhanced diffusion. These polar molecules are going to be attracted to that tip because of the high electric fields. Okay, so the fields and the field gradients are there. They're going to pull those molecules in, and that's a real effect, but it doesn't change the growth. And so that's not right. And why? It's because these molecules will be attracted to that high field because they're polar, and so they'll lower their energy if they can get to that point. So that'll enhance the diffusion. But the molecules in here see no electric field because it's basically a conductor. And so if you take a molecule out of here and put it in here, that also lowers its energy. And so the vapor pressure of the tip is higher than normal vapor pressure. And so this brings molecules in, and this vapor pressure sends them back out again. And so these two effects very nearly cancel, amazingly enough. So that's not right. No good. The real thing is the real explanation, I believe, is an electrostatic effect, which decreases the vapor pressure. So you have a sphere, and you imagine you put a voltage on it. You've got these charges outside the sphere. It's a conducting sphere. And so if you want to pull a molecule out of that sphere, now I'm going to imagine these are non-polar molecules. So pulling a molecule out does not do anything to for the P dot E, because P is 0. But if I pull a molecule out, the sphere gets smaller, and that pulls those charges closer together, and that's not a happy thing. And so this reduces the vapor pressure. So you actually get a bunch of different effects at the same time. You got the Gibbs-Tomlinson effect, which will change the vapor pressure. The polarizability for polar molecules, this electrostatic term for polar or non-polar. And then you throw that in with solvability theory, and you add electrically driven diffusion, which sort of cancels this term. It's a mess, but you can solve it if you make some approximations, which are slightly dubious, but you do what you can do. And you solve the equations, and I won't bore you with a lot of detail, but so we start with a free dendrite, and we put plus V on voltage, and we assume it's roughly a conductor. There's no current flow, so there's no voltage drop. And if you have a low voltage, then solvability, you start with solvability theory at 0 voltage, and that we assume is right. And you add this perturbation, which comes from the voltage, and it causes the growth to get higher, the theory. And this line is a theory. It's got one parameter, but it was not an arbitrary parameter. It was a slightly not known parameter, so we just moved it up and down a little bit to fit through the data. When the tip velocity gets to be twice the normal tip velocity, roughly twice that, then it becomes unstable. The theory blows up, the tip velocity goes to infinity, and something weird happens. And you can get strange things, needles and funny tip splittings and lots of weird stuff. All you know is that the existing theory breaks down and something else happens. And we don't know what happens after that, except weird things happen. And one thing you can, you sometimes get needles coming out. So here's a fun discovery, very serendipitous discovery. This is Vicky Tanashiva in the lab in 1997, that was a long time ago, when we were just getting started. She was a summer student, and she was investigating these electric needles. And we had a really crappy chamber, just a box made out of plastic and metal and sort of thrown together, and really crappy optics. And so she was doing this, and when you turn up the fields and make this happen, you get lots of needles. They come out at kind of random axes. Sometimes they come out along this A-axis, sometimes this funny intermediate axis, don't know what's going on there. And sometimes you get C-axis needles. And we were looking at all this and didn't really know what to make of it. It was very unpredictable. But we really liked these C-axis needles, because if you turn the voltage off, you get a beautiful dendrite crystal growing on it. And this stuff's weird, and we don't know what to do with it, but this is like, well, this would be a great thing to have in the lab. So we started looking to figure this out. And Vicky just did this day after day, tried different things. I mean, usually you run for a day, and then you warm it up and clean it out and try again in a few days. And we had a whole long list of things we could change: temperature, supersaturation, voltage, to try to get C-axis needles. And over again, it just didn't work. We didn't get C-axis needles, and we couldn't figure it out. But then one day, Vicky came and showed me this. There was a needle, and there were 5 C-axis needles, all growing, 5 out of 5. And we're like, well, okay, there's a recipe in there somewhere. There's a recipe for making C-axis needles, and we've got to find it. And we tried and tried, could not figure it out. Summer ended, Vicky had to go back to class, and we said, well, the chamber is kind of dirty. Maybe it's contaminated. We'll just open it up and put some heat tape around there and bake it out for a couple of months and see what happens. So we baked it out, and it got nice and clean, no more smell, and put it back together again and turn it on, and no C-axis needles whatsoever. And so that's when the light bulb goes off. It's like, oh, the contamination wasn't hurting, it was helping. And so then we played around with different kinds of contamination and found out that acetic acid worked out really well. And so all it needed was just a whiff of acetic acid vapor at the right time, and it makes perfect C-axis needles, go figure. And the caulk holding this together, the caulk is a glue, and glues have solvents, and the manufacturers don't want to kill you with the solvents. And what's their favorite solvent? Acetic acid. It's just vinegar, so it doesn't kill you. And so we kind of lucked out there. And so there's our double diffusion chamber. We've got one for making needles and one for making things on the ends of the needles. This is a real leap of faith because I was not convinced you would make the needles here and you could move them over here through a couple of shutters and have anything left. But it turns out it works okay. And so we can model the diffusion in that chamber pretty well. It's got a very nice linear gradient. We've got these stainless steel plates, so we can measure a nice linear gradient, and that's easy to model. It's very stable. So we can estimate. You have to model supersaturations. It's almost impossible to measure it. Just have to model it. It's not like temperature. You can't just stick a probe in. And so we get lots of structures we can see, and we can do these sketches, make morphology models, look at dynamics. The structures were nice because we saw this a lot, and we really had a hard time figuring out what that was until we started doing it on C-axis needles. And here's one we made a C-axis needle, and then some dendrites, and then moved back to needles. And now you can see where the axes were if you roll it around a little. And so we made this model, and that fits pretty well. And you can do quantitative measurements. It's a real research tool now. You can measure growth rates of various pieces. We do these cylindrically symmetric models, and they work to some degree. And we can make all these different things. So we've explained part of it. I mean, the diffusion limited growth gives you this axis. Okay, we understand the complexity. We can't model every detail because it's too hard. But with a computer, you can model dendritic structures, and including dendritic structures over here. And so you can do it. You could do all that. We haven't done it yet. It's hard. But this axis is the hard one, and that requires understanding of attachment kinetics. And that we'll get to in the next lecture. That's my favorite part because that's where the physics really gets interesting. So I have a website, by the way, so everybody likes snowflakes. And there's a book. If you really want to see all the science, you can buy my book. So thank you. We haven't looked at magnetic fields or time-varying fields. Just the DC field is 2,000 volts, and it's very much concentrated by the tip. And you can do a kind of back-of-the-envelope calculation, which shows that should do something. All the other stuff, like with magnetic fields, the same back-of-the-envelope calculation says nothing should happen. But we haven't tried it, and I don't think anyone else has seen anything either. Chemical stuff is quite important. If you put vapor impurities, you can get a lot of weird things going on. And we studied that a little bit and found that we have no idea what's going on, and there's no theory. And so it's really hard to make progress when you have no inkling of a theory. So we can put in various chemicals, and funny stuff happens. Other people have done this over the years, and nobody seems to have any idea how to deal with it. So we kind of step back and so, well, let's try to do pure ice first, pure water vapor, and assume air is inert, which is an assumption, but we think it's a good one. And try to solve that one first. That's already hard enough.
You mentioned that to get in the numerical simulation 2D cases, you have to do anisotropic kinetic attachment.
Yeah.
It is similar to what we do for dendritic growth in liquid, where we have to put the Gibson sum instead of anisotropic Gibson sum. So in your case, you have a real 2D thing. That means you kill all the kinetic attachment in one direction, or how does it work?
Well, we make two-dimensional cylindrically symmetric models because they're easier than 3D models by a lot, of course. But no, the kinetics is highly anisotropic. And the surface tension in ice is very nearly isotropic, so close to isotropic that we can ignore anisotropy. But the attachment kinetics is just wildly anisotropic. So it's very important. Yeah. Oh, yeah, that's exactly right. I mean, for a thin plate, the growth, kinetics here can be 1,000 times smaller than the edge, 100 times easily. So it's quite remarkable. If which would repel each other, I mean, you had two structures. Oh, absolutely. Yeah. I have some movies. I'll show you that in a later talk. But yeah, when two crystals come together, they slow down, and sometimes they try to touch, but they can't quite because they just don't grow. Coarsening. No, that's really slow at these scales. Yeah, if you look at the time scale for coarsening, it's just really long in air, really long. So.